Every time we measure something in the body, a heartbeat, a brain wave, you name it, we're capturing a signal. But that raw data, it's usually just a chaotic mess. The journey from that noisy reality to a clear, life-saving insight, well, that's the whole story of digital signal processing. Okay, let's dive right in.
So this is really the central challenge for any of us in biomedical engineering, right? How do you possibly find that one tiny critical piece of information when it's hiding in a sea of biological noise? Well, the answer lies in this really powerful set of mathematical tools that basically let us talk to signals, understand them, and, most importantly, clean them up.
To start our journey, we've got to begin with the most basic question of all. What exactly is a signal? You can think of it as the language that biology speaks, and our job is to become fluent translators.
At its absolute core, a signal is just a function that's carrying information. Its entire purpose is to be a messenger holding some useful piece of data that we really want to extract. And signal processing, that's just how we learn to read the message.
And look, signals are not just squiggly lines changing over time. An ECG, for instance, that traces heart voltage in what we call the time domain. But an MRI, that's a map of signal intensity over physical space, the spatial domain. And, as we're about to see, every single signal also has this kind of hidden life in the frequency domain, which tells us what it's truly made of.
All right, let's move to the first practical step of our journey. How do we get a signal from the real, messy, analog world of the human body and get it into a computer so we can actually work with it?
See, the world is continuous, but computers, they think in discrete steps. So we have to sample the signal, which is a lot like taking a series of snapshots at very regular, very fast intervals. What we're doing is reducing an infinite amount of data from that continuous wave into a finite, manageable set of points.
But this whole sampling process has a villain, and its name is aliasing. This is what happens when you just don't take snapshots fast enough. A really high-frequency signal can basically put on a disguise, masquerading as a lower-frequency one in your data. It's a classic case of mistaken identity that can absolutely ruin your analysis.
So the crucial point here is, there's a golden rule to defeat this villain. It's called the Nyquist criterion. You absolutely must sample at a rate that is at least twice as fast as the highest frequency you expect to find in your signal. This is the only way to make sure you're capturing its true identity without any of those pesky disguises.
Okay, so once we've safely captured our signal in the digital world, this is where the real magic begins. We need to figure out what it's actually made of. It's time to decode its secret recipe. This slide shows the two fundamental ways we can look at any signal. On the one hand, you've got the time domain. That's what we actually captured. It tells us when things happened. But on the other hand, you have the frequency domain, which tells us what the signal is composed of. It's the exact same information, just presented in a profoundly different and often much more useful way.
Now, this is one of the most powerful ideas in all of science, honestly. You can think of Fourier analysis like a prism for signals. Any complex signal you can imagine, from an ECG to the sound of an orchestra, is really just a bunch of simple sine waves all added together. This technique breaks that complex signal down into its fundamental building blocks, just like a prism splits white light into a rainbow of colors.
The specific tool that does this for us is the Fourier transform. It's our mathematical decoder ring. It takes our time-based signal and gives us back that beautiful frequency recipe, showing us the exact strength of every single sine wave hiding inside it.
So now that we can see the recipe, we can start to clean it up. Let's be real. Real-world signals are never perfect. So let's take a look at how we can isolate the parts we care about and get rid of all the junk.
So here's another challenge for you. The perfect Fourier transform assumes we have an infinitely long signal, but in reality, we only ever capture a small chunk of it. This creates an artificial edge, and it causes the signal's energy to kind of leak or smear across nearby frequencies in our analysis, which just blurs the true picture. The solution is this really clever technique called windowing. What we do is multiply our captured signal by a special function, a window, that gently tapers the beginning and end down to 0. This basically tricks the math into thinking it's looking at one perfectly smooth, repeating cycle, and that dramatically reduces that smearing effect. So let's walk through this. On the left, you can see the problem. Our sharp-edged sample causes that smeared, blurry frequency spectrum. Not great. But then we apply a window function. That's our action, and it smooths out those edges. And the result? Over on the right, you get a much cleaner spectrum with the energy correctly concentrated exactly where it belongs. It's a huge difference.
The other major tool in our cleanup kit is the filter. And it's just beautiful in its simplicity. A filter is basically like a sieve for frequencies. It lets the frequencies we want to study pass right through, and it blocks the ones we don't, like that annoying 60 Hz hum from a power line or low-frequency drift from a patient moving around.
So we've followed this signal's journey all the way from the body into the computer and through our analysis. Now, let's bring it all home and see exactly why these steps are so incredibly critical in a biomedical context.
Every single concept we've talked about translates directly into saving lives. We use filters to clean up an ECG so we can spot a dangerous arrhythmia. We use Fourier analysis to isolate the specific brainwave frequencies in an EEG that might indicate a seizure. Seriously, every time a doctor looks at a crystal clear medical image or a stable patient monitor, they are seeing the direct result of good signal processing.
And that, right there, is the ultimate takeaway. This entire journey is about transformation. It's about taking data that is ambiguous, noisy, and raw, and methodically turning it into something clear, reliable, and powerful enough to make a life-or-death clinical decision. It truly is the invisible engine of modern medicine.
The power of these techniques is just immense. From the smallest neural firing to the rhythm of a beating heart, our bodies are literally filled with signals. And as our tools get better and our understanding grows, it just leaves us with one really exciting question. What secrets are we going to be able to hear next?